In this lecture, we're going to look at how we're going to model a forest fire, right? So this is the spreading of fire is talking about here. Is mostly about simulating how the fire spread throughout a forest. Okay, and it's a pretty interesting concept, and especially in California, um, we see the fires every each year. We see this, right? Sometimes it destroys most properties, and yeah. So the modeling this will help to estimate or at least predict things, uh, how it's going to behave, right? So there might be models out there which is doing that. So in this book, they are proposing to model this in a very interesting way. So first, let's start this. Initially, the concept behind is like this. So we're going to have a forest. Of course, if you take a forest, it will be look like this. Right? There can be trees, obviously, in some areas, right? And so first we have to identify the locations. So that means we have to address this with some kind of the numbering system. So how are we going to do this? We're going to divide this to the rows and columns, right? And these are columns, these are rows like this, and I can throw this in a container which is covering the area like this. Right, so then, yeah, that's good. Now I have my forest inside a grid that I want to calculate things, right? And then we have three categories which we're going to plan on putting things, right? Yeah, if you take a forest, there can be trees, there can be empty land, either those are rocks, right? Or you can consider water or something like that as well. Also empty land which is nothing in there, right? For example, there's a bare land, it's nothing in there. So or it is already burnt by the previous fire, things like that. So those are empty lands. So these are rocks, so the empty lands we can consider as number 0. So this is the forest. We divide into grid, and we illustrate that grid by numbering it. So how do you number this? Is we can have the grid like this. So it's a perfect square we're taking here, right? And if there are trees, obviously I can put 1 1 1. So that's the value for the tree. And if it is empty, we can put zeros. That's the value for empty. And if it is already burning like this, if there's a fast, if it is start already fire, we put 2. So that is what the grid is. This is how it look like in the area, and we divide it to pieces like this and then put some values in it. So this is what the first thing we do. This maybe remind you something that we did in a SIR model, right? SIR model, we have part of this called the burning, right? I mean that means susceptibles, which is a tree, right? It can burn or not, right? Some are immune already infected, that means it's already burning. So the infecteds are here, right? That means here, these guys are kind of that. And the recovered means already immune, or the empty land that has not going to get caught on fire again. So the trees usually can consider as this, right? Susceptibles, right? Anyway, so this is actually a similar situation of modeling. So you can see the connection here, right? But anyway, we're going to look at some other interesting points here. Obviously, you can apply those probability kind of things into SIR models as well. So that is actually that's additional parameter if you really want to put that. In that case, obviously you will see connections, this one and that one, right? Anyway, so let's focus on again on the spreading of fire in a forest. Well, that's what we're going to look at, right? Okay, so let's talk about these two things. These are two terms here. One term says, okay, the probability of tree. So that means what? The probability that a tree initially occupies on a site. I mean, in a site, right? Occupies a site. So that means what is site? Well, site is what we call a one grid, right? So one cell in the grid, actually. One cell. So if you get this one is site. Okay, so that's what site is. Okay. And the probability of initial density, or the initial tree density measured as a percentage. What does that means? Okay, I tell you example. It's better you understand. This is much better to go further, right? So if I have 100 by 100, great. So that means what? Okay, I have total cells I have is 10,000, right? 100 on this, 100 on this. And then let's say I have 3,000 out of 10,000 cells, 3,000 of them has trees. So that means number ones, I have 3,000 of them, right? So the probability of having a tree is this. So how do you put this in a percentage? Well, simply let me address it this way. If 10,000, right, if it is 10,000, you have 3,000 trees. If it is 1, you have 3,000 divided by 10,000 trees. What does that mean? Well, to make it convert to 1, obviously I had to divide both sides by 10,000, right? So this will give you, if I cancel this one to this one, oh, let's leave it like that for a minute. And then if it is 100, so how do I make it 100 here? I multiply this by 100, I get 100. So that means if I do something to that side, I have to do that the same to this side. This is your initial value multiplied by 100. So if you cancel out all the zeros, 2 zeros go to this guy, 3 zeros, right? I don't have 3 zeros. I have only 2 more to cancel this. So I get 30, right? So that means 30% of my cells have trees in it. 30% of. So that's what it means, density measured by the percentage. So out of this whole area, 30% of that occupied by trees. So that's what it means if I calculate it in this way, right? Okay. Right, so that is the probability of having a cell. If you get to pick one cell, the probability of having a tree in that cell is what? 0.3. How do I get that from here? Well, this means 30,000 divided by 100 is what this means. So this means if I get a 0, 0 cancel out, 3 divided by 10 is this value. So this is the percentage of the probability of having a tree in a picking cell, right? Right, so then the other probability I'm talking about here is the burning. Okay, so in order to burn a tree, it has to have a probability of, first it has to have a tree in there, and then out of that there has to be another probability that you can apply whether the tree is burning or not. So that is also a fraction of whether is it possible to burn it or not, right? So how do you come up with these values? Well, the probability of burning, actually it has to be man-made or collecting by the statistics. Are there burnable trees or not, that you have to consider that. Okay, right. And right, so let's move to the next step. So now you have two values here, and we're looking at an algorithm here. So what is this algorithm does? Well, in this algorithm we going to initialize the forest. So that means, yeah, this part right here, maybe you can collect by the statistics. if there is really a fire happening, obviously you can get the statistics from that. But we don't have anything like this. Because of this is a real-time simulation. If it is really going to get fire, we're going to simulate one. We're going to create one here and see how we're going to address this, right? So this is actually imaginary, right? Virtually you're going to create a grid. So how am I going to do? What is this whole thing talking about here, right? Okay, so we have an n by n grid. So let me draw it here. So I have n by n grid, right? This, oops, it's too low, so you cannot see it properly. Let me draw it here, right here. Okay. So this is the tree. The grid. So that is the n by n grid. So that means n cells on this side, n cells on this side. Okay. And then what it says, this is what I'm going to return at the end, but it should contain some values in there. So I will have some values fill up with it. So how do I fill up these values? So that's what we're going to look at next. But anyway, this is the grid I have, and it should have zeros, ones, and twos fill here, right? So how do I really going to fill zeros and ones and twos in this? So that's the next question, right? So that's what it's talking about here. So we have the precondition n by n grid. So this is what I have, and it is a square, obviously. And the tree is a probability that you have to give two more inputs. One is a probability of having a tree. So in this case, we just did the example, and we got that as a 0.03. It's a probability, and you pick another value for this one. Let's say 0.1 or 2 is the probability of the trees burning. That is too much though, too big value. You can take a smaller value if you want. That's saying the tree is burning, right? So how do I take care of it? So I will move on one cell to the other, and then I throw a random number. Why I'm throwing a random number? Because I don't have the data, right? I'm just making a simulation here. So the random number, if that number is less than a tree, so that means what? These random numbers has to be between 0 and 1, right? Otherwise it will be greater than the probability. So how do I do that? Well, I can call it rand a number. Let's say this one is mod by n value and divided by what? So whatever the value I get here, divided by maybe n by n, right? Or something like that. So if you divide it by a value like that, or maybe divide this, so it's always has to be less than n though. So I can divide the value by this. Yeah, so this is enough. So you get a value, and it's a remainder, and divided by n will be always less than 1, right? Okay, so you don't need n by n, so just have one n there. So this will give you less than 1, and then so that if that number is less than probability of a tree, so that means if it is less than 0.3 in this my case, there will be a tree in this cell. So I can have the tree in that cell. So like that, I'm going through one cell by one, and then I'm just marking those. So what is the value I'm putting? Actually, I'm not going to circle it like this. I'll put 1 there, right? 1 there, right? If this satisfied, if this condition satisfied, and there's a tree in it, and then I'm throwing another number, another one like this, and see whether is it less than the probability of a burning. So that means if there's a tree there, of course that satisfies the first condition, and if there's a tree there, then I'm considering whether is it burning or not. So then what I can do is I can put 2 if there's a tree here. So I can change this value to 2 actually. Right, so that is burning, right? Okay, so those are 2 conditions. So I fill up 2 numbers already. One is the burning ones, one is a tree, right? Right, so what are the trees which is survive from not burning? Well, the second random number, if it's greater than burning tree, it will remain as 1, right? And then if it is not falling into any of these, so that means my first number here is greater than probability of a tree, then I consider this as empty. So that means I can put zeros without any problem. Okay, so that's how you just initialize this condition, and we'll apply a time step to calculate the rest. But first we have to calculate this in this manner and have just the initial grid with some values filled in, right? Okay, so then what you do, I just create my imaginary forest here, and it is look cool now. We have 3 numbers in it. Right, so then you have to update it. So in this case we consider this as updating rules of the next step. So some rules we're gonna apply here, right? So these are the rules. Let me talk about it up to here, right? So what are we doing here? Okay, the first thing is apply function spread to each cell, determine the value. Okay, so we already have our initial value is the empty tree or the burning, and then you move to the next step. So how do I move to the next step is here I'm going to use the von Neumann neighborhood model. So what is that? Well, in the diffusion we talk about something called Moore's model or the von Neumann. So the von Neumann said what? Well, he said, well, if you want to consider spreading heat throughout the system, you pick only the neighbors. So if I'm here right now, he become only 4 neighbors, which is sharing the same edge. So if this guy is sharing these edges right here, right, and then I consider this one, this one, this one, and this one, and this one. So those are the only things that can spread the fire from here, not the diagonals. So this is actually no touch actually. When it's come to the forest, it makes sense, right? So you cannot actually not consider it like this. So it will be touch with a bigger cell size, and the edges like this might you consider as a spread of fire. So this is why the von Neumann argued that this is the better way of doing it. But we talking about the metal bar, it's come to the atoms level. It's not like a tree level, it's an atoms level. In that case we consider for all 8 cells around it. But in this case it's the big trees, and so if it is touch each other with enough distance, enough space on a width or a height, in that case we consider that cell can spread, otherwise no, right? So that's why the von Neumann is a suitable way of handling this. Okay, so what are things there? The rules we're setting here is if the site is empty, it remains empty. So if it is, this one is empty or the 0 is never going to change that value. It will be the same for the rest of the simulation, right? And if it is 1, actually, if it is 1 here, that means it can change to 2. Only if it is fire get caught, right? So that is a possibility, and we're going to set this as 1 to 2, right? Okay, and the third condition they're saying is if it is already burning. So if it is, this one is already 2, in the next time step this will return to 0. That means all the trees in that cell is burned already. There's no way that you can move further, right? So in that case, if I have one like this one goes to 0. I can recall again the SIR model. If you are sick and then you get immune, you won't get sick again. So it's the same thing. So you have antibodies already. So same idea here, right? 2 to 0. Okay, right. So those are the rules we are applying in this simulation. But there are two. This is too lame. I mean, we have something like very basic now. So we're going to make it a little bit spice up. I mean, adding some more parameters, right? the realistic parameters, of course, right? What we can do here. So we're going to apply two more conditions to make it more complicated. So what are the conditions we applying here? Well, one can argue if there are trees, right? If there are trees, obviously this tree can get caught in fire very easily. But if you have made tiny little ones like this, maybe they are related close to like this. Maybe this one get caught on fire, but this is not. Or maybe you have a swamp kind of thing, and then there are trees there. There's water around it, but it's never going to get caught on fire, and things like that. Or maybe you have rocks around, and then little trees survived around because of that. Won't get on fire. So in that case, there's a probability of immune. Even this one can't get caught on fire, these won't. So in that case, we can consider some of a probability. We're going to throw in there and say, okay, there's immune trees. They won't get fire ever, even in the next step. So that's what we're going to put it here. And the next one is pretty interesting and really bizarre condition we just applying here, right? So what this means, we have some in this forest. We just consider there's a lightning always happens. So what this means is actually not lightning applying here. This means if I have fire here, there can be a possibility that I have fire somewhere else as well. Right? In this grid, there can be 3 fires in 3 places. So this is what, this can suddenly start fire here. Even I was addressing here. And then again, it can be here. So how do I just justify this case? Is we say the probability of lightning. So that's why it is put in there. It's not like actually is lightning happening in the reality. There can be other causes to start fire. So if the lightning is there, there has to be rain as well. So in that case, this immune probability goes high, because if the tree is wet, it's never going to get fire. If the ground is wet, it's very hard for fire to spread. Right. But anyway, so the meaning of this probability of lightning is you just consider your fire in the grid happening in several places. That's the idea. Okay. Right. So it's not like actually there has to be a lightning all the time, right? So that's just to give you some idea of it. Okay. So now how we going to address those two, right? So this is what the separate rules we have to apply for those two cases. One is for the first situation involving neighboring burning tree, we employ the following logic of it. So what is the logic here? We say, okay, there's a tree, and we say consider the neighbor of it is burning, right? And then you throw a random number and consider that, okay, if it is less than probability of immune, you return a tree, right? The other was the probability of burning. So what this means is I will set up something look like the rule I'm going to set up here is I have my grid, right? Let me take this one as this. Okay. The rule is I'm considering this one. So this is my site right here. Okay. And if my one of these, either this one, this one, this one, or this one is burning. So it has to be either 1, 2, 3, or 4 is burning, right? Only a surrounding it. And then I throw a number. So I'm throwing a random number and see whether that number is falling into less than 1 probability, right? And then if it is really less than 1 probability, then I consider this one is immune, right? So it is immune means whatsoever, it's not going to get caught on fire. So it will be safe even you have surroundings of fire. So in this case, this will remain as number 1 forever, as long as the random number is less than immune probability. Otherwise, obviously, you have to change this to 2. So that's the condition we are applying for those rules when we're simulating this, right? So that is one thing. Okay, so then, right, so that is the basic things that we do. And how we really going to simulate this, or the periodic boundary conditions that we're going to apply. This is also called grids expansion. So what is this doing here? They're talking about is extend new rows and new columns, and then go move on further. So let me talk about this for a minute. So this is one thing that we might interest you in this case. Let me have a little bit bigger pen type, right, so you can see better. Right, so now this is my simulation. Right, so this is my set of things, the cells, I mean, right? Okay, so now I set up at the beginning I will consider only a very few areas of it. So that means let me tick this guy, right, and its neighbors. For example, this one has a fire, right? This one has a fire, and this is not, and things like that. So and let me take it to the middle, so it will be easy for you to explain this, right? Okay, so now this is the area I'm considering right now, right? Okay, this is the area of fire, and then no fire, and then all these things happens. So how do I spread this to? How do I spread this to this, 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 this? All this area here, here, and then here, and then here. How do I really gonna apply whatever happens here to your surroundings, right? So this is the idea they're proposing here, right? So this is not like you are adding more to your container. It is about your condition that you are applying here, and expand this to the next boundary. So what you do is, I get these values right here on this bar right here. Okay, I take these values and copy it to this bar right here. So that's what it does. And then again, I take these values right here, these values right here, and copy it to this bar right here. So in that case, what? I have now spread my conditions to my neighbors. You can do it from this side to this side too, right? So this means I'm having a small square now. Next time I will have bigger square. Next time I will have bigger square. So this is the situation of the fire. Now it's spreading through the areas around it. So this is how you apply expansion of fire around the grid. Okay, so if I have something here, if I don't have anything, if I have something on this for the columns and rows, if I want to spread this, I take these values right here, copy it to here. I take these values right here, copy it to here. So it will be expansion like that. So this is what it's explaining here, how we go through expansion on this case, right? So that is one thing when you're talking about expansion, how in through this grid. Okay, so then so the define a function periodic latitude using the periodic boundary conditions extend to the square lattice on the cell direction. So that means what? The expansion, that's what they're talking about here, the same thing that I was talking about. The function accepts the grid of extended cells directing on the latitude of the grids. So so the same thing that I just said, you copy rows and columns separately, and then this is the other way around. So you get this column and copy here, and you get this column and copy here, so you can have a spread of fire on the cell. So that's what we call latitude, right? And then the function spread the fire need to be probability. So there's a typo right here, it says be fire of lightning and immunity. So this is the whole thing. So the preconditions, you will have burning trees, lightning, which means the fire happens, and then immune trees that you will have, and then the spread is how you're going to update your rules for the grid, and then you returning as the result, you returning your the answer, and then also we have the forest extended the areas by using a periodic latitude, right? So that's what it does here. And yeah, so that's the whole thing that I was talking about. I already explained this whole thing, and you put that into one function, so that's what it's showing here. That's the algorithm, right? So then what happens at the end? So initially, so this is so I can say, let me pull this up a little, right over here. So the timestamp initially, what you do is, this is the initial function that I was explaining. So if you have initial value, of course you can see now I have only one place of fire right here, and these empty places are empty with no trees, and the rest is have trees. And then you're starting from here, and yeah, so next timestamp, so we consider only this part, and then you spreading that using that little cell expansion, right? So copying these things here and here, copying these things to here and here, you can see now it's expanded to this, and then you applying next timestamp. So here you can see now I set up another fire here. That means what? There's a lightning probability cause somewhere else, right? And then this one is anyway spread through to this area. Now it's bigger, so now you can again looking at columns and rows expansion, right? So when you do that to two places now, right, and then this one is expanding too, right, and this one is going down a little because of the empty land, I guess, and then it's going up. So here again it's spreading and again spreading, right? So you can see now the simulation is start picking up, and it's showing some spreading of fire throughout the system. And after this is only t equals 5, and if you jump up to t equals 15, so that means the time is going up. So you can see these things are increasing rapidly. So you can see now values here has gone up really big values, right? So and then this is the simulation. After several frames of running the simulation, you can see this, right? So yeah, so what you have to learn or remember on this one is nothing much actually. There's no calculations on this one. Just have a good idea how do you spread the fire, so which means this one, how do you spread through the cells, and the other one, how do you initialize the things, what are the things we consider in that case in up here, how do I initialize this, right? And one more, what is the neighborhood type we pick, and interestingly how we apply these to immune and the lightning also into this simulation. So that's pretty much what we are expecting you to know on this one. Okay, all right, so the last one is ant movement. So we're going to look at that after this, and then we call the semester, and then we will have finals. I believe most of the people have a good idea what you have to submit on the project. And right, I'll see you on the last lecture.